Hi all, thank you for being here today for our fourth CosmoVerse online training series session with Dr. Laura Herold. Thank you, Laura, for accepting our invitation today. CosmoVerse, as you may know, is a network of over 400 researchers in Europe and over 600 globally, with the aim of unifying efforts in confronting the question of cosmological tensions and understanding how different parts of physics can contribute to that effort. Dr. Herold is currently a postdoctoral researcher at Johns Hopkins University in Baltimore, in the US. She obtained her PhD from the Max Planck Institute for Astrophysics in Garching, Germany, under Professor Eiichiro Komatsu. She then went on to take on a postdoctoral position at the same institute, where she worked on various dark energy models, including early dark energy, and where she won the Kippenhahn Prize for Best PhD Publication, among several other awards. She has been involved in leadership activities, such as lecturing and mentoring duties. In this fourth session, she will present to us the latest approaches toward going from ΛCDM to early dark energy. Laura, please start in your own time. Thank you.
Thank you so much for the nice introduction. And yeah, also thank you to the organizers for having me in this training series. So yeah, welcome to the lecture from ΛCDM to early dark energy. The plan for today is to start very basic and repeat some basics of the ΛCDM model, then go over to the Hubble tension. Then we can have a 5-minute break. And then in the second part of the lecture, I will focus more on early dark energy. And in the last 5 minutes or so, I will introduce you to some notebooks that you can do as self-guided homeworks. And these will help you to get familiar with Baltimore solvers like class. And I really recommend to do these notebooks because I think they're actually fun and you don't need to install anything. You can do everything on the cloud. So yeah, I think you might even learn more from the notebooks than the lectures. So the outline of the first part before the break will be to start with a basic introduction, where we'll introduce the basic equation in a homogeneous and isotropic universe, which are the Friedmann equations, and then discuss the matter content in the universe and how to define distances in an expanding universe. Because we will need all of those concepts to discuss the Hubble tension later. And in order to understand the Hubble tension, as you know, the discrepancy is most severe between the CMB measurement and the distance ladder. It's very important to understand how the CMB actually constrains H0. So we will discuss that. And then we will discuss solutions to the Hubble tension. So let's start with a very condensed crash course on cosmology to get everybody on the same page. The basis of cosmology is general relativity. And I will not go into any details here because there's a long lecture of Matteo Martinelli about this topic. But yeah, the centerpiece of GR are the Einstein equations, and they basically describe how matter tells space how to curve and space tells matter how to move. So the right-hand side has the energy momentum tensor, which describes the matter content. And the left-hand side has the metric, which describes the geometry. And so after these Einstein equations were written down, many people were, of course, interested to find solutions for these equations, especially solutions for the universe as a whole. And to find solutions to these very complicated equations, they used as a guiding principle the cosmological principle, which is very well founded from observations, especially the cosmic microwave background. So this principle states that on sufficiently large scales, the properties of the universe are the same for all observers. Or equivalently, the universe is spatially homogeneous and isotropic on large scale, where homogeneous refers to that something is the same in every point. Isotropic refers to that something is the same in every direction. And so I illustrated this in this picture here. So on the left-hand side, you could say this picture is homogeneous because it has a cat in every point, but it's not isotropic because there's a preferred direction because all cats walk to the right. Then on the right-hand side, the picture is isotropic from the center, but it's not homogeneous because it looks very different in different points. So finding, so Friedman, Robertson, and Walker, they wrote down a metric for a spatially homogeneous and isotropic universe, where the line element that one can use to measure distances in a space-time is given by dt squared, where t is time, plus this a of t, which is a very important quantity in cosmology. It's the scale factor that describes the overall scale of the expanding universe. And the convention is to set the scale factor of today to 1. Then there's another important variable, which is k, the curvature parameter, where k equals 0 for a flat universe, which is the observationally preferred case. And flat means if you imagine light rays that start off parallel, they will keep being parallel. This is different in a spherical universe where you would have k equals 1, because light rays that start off parallel, they would converge to each other and they would cross at some point. Then you can also have k equals -1, which is a hyperbolic universe where light rays that start off parallel would diverge from each other. Then another ingredient that one needs to solve the Einstein equations for a homogeneous and isotropic universe is to define an energy momentum tensor. And the energy momentum tensor that is compatible with homogeneity and isotropy is a perfect fluid. And this perfect fluid can be completely characterized by its energy density and pressure. So the energy momentum tensor looks like this, with rho being the energy density and p the pressure, and u mu is the fall velocity of the observer. Now inserting this energy momentum tensor and the FLRW spacetime metric into the Einstein equation gives the famous Friedman equations. And these describe how the expansion rate, so how the scale factor of the universe depends on the curvature, the energy density, and the cosmological constant. And there's a third famous equation that one gets by inserting the second Friedman equation into the time derivative of the first Friedman equation, which gives the continuity equation. And this describes how the energy density of the universe changes with the expansion. Now, this row here in the Friedman equation is the total energy density of the universe. But it's very common to define rho k, so interpret the curvature also as the energy density, and rho lambda, so define an energy density of the cosmological constant. So one can rewrite the first Friedman equation in a more condensed form, so that the scale or the expansion rate just depends on the total energy density of the universe. So in the lambda CDM model, this total energy density is composed of different components of radiation, matter, the cosmological constant, and curvature. But from observations, mainly from the cosmic microwave background, we know that curvature must be very small. So we will neglect it from now on. Now in an homogeneous and isotropic universe, the components can be completely described by a linear equation of state where the pressure of the component is proportional to the energy density. And the different components, they have different equation of state parameter W. So dark matter and baryonic matter, they are pressureless, so W is 0. No photons, radiation, and neutrinos, they have pressure, so W is 1/3. That also lets them redshift faster than matter. And then there's dark energy, or the cosmological constant, that has W equals -1. So in a sense, negative pressure that leads to the expansion of the universe. And inserting this equation of state in the continuity equation lets us rewrite it in a more convenient form. And using this equation, one can directly describe the energy density of the universe as a function of the scale factor, and we will need that later. And the convention here is to have a subscript 0 in order to refer to the current time today. So as we said, the first Friedman equation describes the rate of expansion as a function of the energy content of the universe. And this is nothing else but the Hubble parameter. So the Hubble parameter is A dot over A. And the Hubble constant then is the Hubble parameter today. So the Hubble parameter at t equals t0. And this is a parameter that we will talk about a lot later in the context of the Hubble tension. So inserting the Hubble parameter in this equation, we can define a critical energy density, which is the density of a flat universe, so universe without curvature. If we have k equals 0, it's simply the total energy density of the universe. And inserting this in this equation, one can bring the h0 on the other side, and then we can write this Friedmann equation in a very condensed form. Moreover, it's useful to define these fractional energy densities, the omegas, where omega I is some component like radiation or matter, is given as the energy density divided by this critical energy density. And using that, one can even condense the equation further. And using the time evolutions of the different components like radiation, matter, and curvature, one can write this as a function of the scale factors and introducing the redshift, which is 1 plus c equals the scale factor today over a, we can finally rewrite this in the very famous form that we will use a lot later, where h squared over h naught squared is given by the different components with their redshift dependence. So from this, we can directly read off that radiation dilutes with 1 plus the redshift, where matter dilutes with 1, like to the power 4, and matter with 1 plus the redshift to the power 3. So radiation dilutes faster than matter, dilutes faster than curvature, and omega lambda is constant since it's a cosmological constant. And here we always wrote a subscript of 0 when we referred to the current time, but it's often just omitted so that omega I actually denotes the current energy density of the universe. So people simply write the explicit time dependence if they wanted to refer to the time dependent quantities. And now I want to switch gears a bit. So in an expanding universe, it's actually not straightforward to define distances. There's two very natural ways to define coordinate systems and measure distances. The first is a co-moving system that expands with the universe. So if you imagine that you have two galaxies, they start off with some coordinates and they keep the same coordinates even though the universe is expanding and their distances are growing. Then a second coordinate system that's very useful is just to have a fixed coordinate system where the universe expands within that coordinate systems and objects actually drift apart with the expansion. And now we want to relate a physical distance, so an actual measurable physical distance, with the scale factor a. And now to get an expression for the co-moving distance psi, one can consider a photon traveling at an infinitesimal distance rp, where we know that a photon travels at the speed of light. So since we work in natural units here, the speed of light is 1. So we can compute that by dr by dt. And now if we insert the expression for r here, we have a d psi by dt. And now basically doing separation of variables, we can integrate over t to get an expression for psi of t. Now inserting again the redshift, we can write this in, we will use a lot later, that the co-moving distance is given by an integral over redshift divided by the Hubble parameter. Right now we talked about co-moving distances and physical distances, but it's very convenient to define the so-called angular diameter distance, which one can directly infer from observations. And the angular diameter distance is defined such that this very natural equation holds, such that an angle can be computed by dividing the size of an object by the distance of the object. So this is basically the small angle approximation that we require to hold also in a cosmological constant, even in expanding universe. And the expression for the angular diameter distance is simply the scale factor times the co-moving distance. And to derive this equation for dA, one can consider that the proper size of the object is actually given by the co-moving size times the angle, which would be the co-moving size of the object. And then one simply can multiply the co-moving size of the object by the scale factor A. And this gives one, if one inserts this in this equation here, one brings the A of t on the other side and gets this equation. So how to solve the Hubble tension now? First of all, let's introduce the Hubble tension. So the Hubble tension is a discrepancy between different measurements of the current expansion rate h0. And it's most severe between the cosmic microwave background measurement, which is an indirect measurement of h0, because the CMB constrains the composition of the universe at early times and needs to assume a cosmological model in order to infer the expansion rate today. And since the CMB constrains the composition of the universe so well, this is a very precise measure of the expansion rate, but it is model independent because one needs to assume a model to predict the expansion rate today. There's also other indirect measurements, like using baryon acoustic oscillations that we will discuss later, and using galaxy clustering. Then on the other hand side, there are the direct measurements of h0, which are based on distance ladder, for example, Cepheids, TRGB, that are used to calibrate supernovae. One can also use strong gravitational lensing. And these approaches are typically less precise due to the astrophysical modeling, but they are independent of the cosmological model. So it's really two different types of probes that are in tension here. So how can we, from a theorist perspective, solve the Hubble tension? This general strategy to solve the tension is to assume that the direct measurements are correct, and to change the cosmological model in order to infer a higher h0. So basically, our goal here is to change the model such that from CMB we get an h0 of 73 kilometer per second per megaparsec. But in order to get a higher h0 from CMB, we need to understand how the CMB does actually constrain h0. So the CMB provides the most important cosmological probe when it comes to constraining the parameters of the cosmological model. So to bring everybody on the same page, here's an illustration from the WMAP collaboration of the history of the universe. So in the early universe, the universe was very hot and dense. And the idea is that quantum fluctuation during inflation actually led to density perturbations that expanded with the expanding universe. Once inflation ended, the universe expanded at a slower pace and cooled down. And once the universe cooled down enough such that electrons and protons could form atoms, light was suddenly free to travel. And this is what we see today as an afterglow of this very hot universe as the cosmic microwave background. And after the CMB, the universe expanded at a slower pace and galaxies and stars formed. And then at late times, something else interesting is happening, that the dark energy leads to an accelerated expansion. So this is what the sky looks in optical if one is in a very dark place and on the southern hemisphere, such that one can see the galactic center. And this is what it would look like if we had ice in microwave. And I actually literally downloaded the 70 gigahertz Planck map without any processing. And this is what it looks like. So one can clearly see the galactic plane in microwave. So if we professionally mask the galactic plane with this white box, we see that the microwave sky is basically a constant temperature of about 2.7 Kelvin. Now, if we crank up the contrast, we can literally see the CMB. And this is the image from the Planck collaboration with some proper foreground cleaning and inpainting. And here you can see that while the CMB is almost constant at 2.7 Kelvin, there are tiny fluctuations at the level of microkelvin. So how can one analyze CMB maps like that? The most common strategy is to decompose the temperature fluctuations into a set of waves with various wavelengths. And then the second step is to plot the strength of each wavelength, which gives the power spectrum. And in one dimension, we're very familiar with that because decomposing into waves in one dimension is the Fourier transform. But on the unit sphere, decomposing into waves corresponds to the spherical harmonics decomposition. So what we do is we start with the map on the left-hand side, where the map can be described as temperature fluctuation as a function of the angles theta and phi. And these temperature fluctuations, they can be expanded in terms of these spherical harmonics functions and coefficients ALM. And the ALM contain exactly the same information as the map. So the spherical harmonics function are a fixed function that one can look up on Wikipedia, basically. And the ALMs, they contain the information from the map. Now L defines the multipole, and the higher the L, the smaller the scale. And now the power spectrum is given by basically averaging over the M values and taking the absolute value square of these ALMs, because the ALMs are complex functions. And this gives a real function the power spectrum, or just also called the CLs. And this is what they look like from the Planck collaboration. It's very common to plot, instead of the CLs, plot the DLs, which is simply L times L plus 1, because this shows better the scale of every variant part of the power spectrum. Now that we have these red data points, how can we analyze data like that and get cosmology out from this data? So to predict the CMB power spectrum, one needs to solve the full fluid equations, which are the Boltzmann equations, for all components of the universe. And this can be done with cosmological Boltzmann solvers like CAMP and CLASS, which you will hear more about in the notebook homeworks. And these Boltzmann solvers, they take as input the lambda CDM parameters, and they can be sampled within MCMC samplers. So the lambda CDM model has the basis lambda CDM model has 6 parameters. And little omega CDM is typically defined as h squared omega CDM, which is the physical energy density in cold dark matter. Then omega baryon is little h squared times the fractional energy density in baryons, which is the physical energy density in baryons. Now this little h is the dimensionless Hubble constant, which is simply h naught divided by 100 kilometers per second per megaparsec. Then there is tau Rio, which is the optical depth to ionization, which is basically a measure for how often the CMB's photons scatter from the emission to us. And then there's AS and NS, which is the amplitude and tilt of the primordial power spectrum as predicted from inflation. And yeah, if you do the exercises later, you might find this useful. So we already saw the CMB power spectrum, but of course the most distinct feature are these wiggles here. So what generated the wiggles? The wiggles are the so-called baryon acoustic oscillations, and they are generated in the very early universe, when the universe was a hot plasma of baryons and photons. And the belief is that small density fluctuations are generated by quantum fluctuations during inflation. And in places where there's a little bit more matter, gravity attracts even more matter. So overdense regions get more and more overdense. However, since the photons and the baryons are tightly coupled, the photons have pressure. So once these overdensities get too dense, the photon pressure will drive them apart. And if you have a driving force and a restoring force, you will find some oscillations. And you can imagine this like raindrops on a water surface. So the quantum fluctuations are basically the raindrops, and they lead to some initial perturbations on the water surface. And now, as on the water surface, you have a driving force and a restoring force, and you will get waves. And since there are many quantum fluctuations, these waves overlap all in space. So we cannot see distinct waves, but we see an overlapping pattern of many waves in the CMB. And once the electrons and photons recombine, the photons can travel freely. And this is when the density waves freeze. And we can basically see a frozen picture of these density waves in the CMB. So now that we know that these baryon acoustic oscillations, these wiggles, are from traveling sound waves, basically, we can compute the co-moving distance that these sound waves in the early universe traveled. And this is the so-called sound horizon. We know that the sound waves, they started traveling at the Big Bang until the time of recombination, which is denoted as T star. And T star, or recombination, is the time when the protons and electrons combine and the photons can travel freely, and this is when the CMB is sent out. So we can simply obtain RS by taking time times velocity like we would do normally. But since the sound speed depends on time, we need to integrate over the sound speed. However, there's one small complication. While the sound waves travel in the early universe, the universe expands. And this slows down the sound waves in the co-moving coordinate frame. And this is expressed by basically this ratio of the sound speed divided by the scale factor of the universe. So this factors in the expansion of the universe while the sound waves travel. So we have the co-moving sound horizon, and now we want to rewrite this co-moving sound horizon. We can use the fact that we know that dA dt is simply a dot. So we rewrite this integral as a function of the scale factor. Then we want to rewrite it is in terms of the redshift. So we know that the redshift derived by the scale factor is simply 1 over a derived by a, which gives this minus 1 over a squared. And we can insert this in this integral. And simplifying this, we can identify the Hubble parameter here. We get the most common expression for the co-moving sound horizon, where we can compute the co-moving sound horizon by integrating the redshift from the redshift of recombination to the Big Bang over the sound speed divided by the Hubble parameter. And now one missing piece here is the sound speed. So from experiments on Earth, we know that the sound speed in a plasma is about 1 over square root of 3, the speed of light. But here there's a small correction coming from R, which is the baryon photon ratio, and is given by this expression here. So now we have basically all the pieces together to compute the co-moving sound horizon. And the thing is, what we actually observe is not the physical sound horizon, the physical size of the sound horizon, which is depicted as this ring here, but we measure the angular size of the sound horizon. So we measure this angle theta because the CMB we see as a sphere on the sky. So all we do is measuring angles, basically. But we can relate the angular size of the sound speed by dividing the physical size of, the angular size of the sound horizon is given by the physical size of the sound horizon divided by the angular diameter distance. And the angular diameter distance we already discussed before is given as this integral from today to the redshift in consideration, integrating over 1 over h of z. And here we're sometimes switching between the physical size of the sound horizon and the co-moving size of the sound horizon, but one can simply convert between physical coordinates and co-moving coordinates by using the scale factor. So ultimately, we wanted to talk about the Hubble tension. So how does the CMB constrain H naught? So it constrains H naught over the angular size of the sound horizon. So basically over the distance between those wiggles in the CMB power spectrum. And as we said, this is given as a ratio of the physical size of the sound horizon divided by the angular diameter distance. And these are expressed as these two integrals where both of them depend on h of z. So cosmology mainly enters over h of z here. And as we derived earlier, h of z can be written as h naught times the square root of the components of the universe and their respective dependence on redshift. So now if we can get omega radiation, omega matter, and omega lambda from somewhere else, this equation becomes an implicit equation for h naught. So now the question, how does the CMB constrain h naught, reduces to how does the CMB constrain omega radiation, omega matter, and omega lambda. And so omega radiation is actually very easy to get because omega radiation is related to the temperature of the CMB by the T⁴ law. And the temperature of the CMB has been measured very precisely by the FIRUS experiment on the COBE satellite. So by simply plugging in the temperature of the CMB, we can already determine omega radiation. And this is also why omega radiation is basically fixed in all analysis because it has been measured so precisely already. Then how can we get omega matter? So actually the CMB is not sensitive to capital omega matter, but to little omega matter. So the physical energy density in matter. And this quantity can be obtained from the height of the acoustic peaks. So θs is basically the distance between the acoustic peaks, but one can get omega matter as the height of the acoustic peaks. So here in this plot, I show that if you have higher omega matter, you get lower peaks of the CMB. And this is the so-called Sachs-Wolf effect. So yeah, from that, we can get omega matter independently of H. And then how can one get omega lambda? Now, since we assume that the universe is flat and k equals 0, in a flat universe, all these energy densities are related by this closure equation that omega radiation plus omega matter plus omega lambda is 1. So by having omega radiation, omega matter, one can simply obtain omega lambda. So now, basically, we have all ingredients that are needed to directly infer h naught from θs. So now, how can we use that information to resolve the Hubble tension by modifying the ΛCDM model? So as we said before, what we actually measure with the CMB is θs, so the distance between the acoustic peaks, which is given as a fraction of the physical size of the sound horizon divided by the angular diameter distance. Now, as we said, θs is precisely measured by CMB, so θs is assumed to be fixed. So there are two options to solve the Hubble tension. One are the so-called early time solutions. And these solutions, they modify the universe between the redshift of recombination and the Big Bang. And then on the other hand side, we can modify the denominator. These are the so-called late time solutions, and they somehow affect h of z between today and the redshift of recombination. Now let's have a look at the late time solutions first. So they modify dA between today and the redshift of recombination by modifying the expansion rate in this redshift range. So by modifying h of z. Now we can have a look at h of z at late times. At late times, radiation is pretty much negligible because we are in matter domination. And therefore, h of z can be expressed simply as a function of the omegas and h naught. And now the problem is that we have lots of observations of h of z and omega matter of z coming from galaxy baryon acoustic oscillation data and supernova data. So it's very challenging to increase H0 enough. So you can have some small impact here, but it's challenging, and there's a lot of constraints to get that working. But there are some approaches, and I think they are discussed in other lectures. So I'll leave the late time solutions to them. Then there's the early time solutions, which modify RS. So if we look at the formula for RS, there are three options to do that. One can modify the redshift of recombination, C star. One can modify the sound speed, ZS, or one can modify age of set. Now, all of these three things have been tried, but the easiest by far is to modify age of set. For example, by introducing an energy density which boosts the expansion rate before recombination. Now, if we have a look at age of set at early times, we can set the cosmology constant to 0 because cosmology constant only starts to become important at very late times. So age of set is given by this formula. And the idea here is to introduce some additional energy density, so introduce an additional omega, which increases age of set at early times. And now if we increase age of set at early times, this leads to smaller physical size of the sound horizon, RS. So this whole quantity becomes smaller. And one of the arguably maybe most successful ideas is the early dark energy model. So what's the idea behind early dark energy? So as we said, theta s is fixed by observation. It's given by the distance of the acoustic peaks, and it's measured with 0.03 precision by Planck. So what early dark energy does is it introduces an additional component before recombination that reduces RS. So we said H of Z is increased by early dark energy at early times. So this H of Z increases. That means this whole term becomes smaller. So RS becomes smaller. Now, because theta s is fixed by observation, if RS becomes smaller and theta s is fixed, also the angular diameter distance has to become smaller. So because theta s is fixed, the angular diameter distance decreases. And if we look at the formula for the angular diameter distance, it mainly depends on h of z. And if we assume that in the early dark energy model, the energy content is similar to lambda CDM, the easiest way to get a smaller dA is by increasing H0. And therefore, H0 decreases in early dark energy models. And this is what we were aiming for in resolving the Hubble tension. Okay, so this already brings me to the recap of the first part of the lecture. So in the first part of the lecture, we had this very condensed overview of the Friedmann equations, Hubble parameter, and how to define distances in an expanding universe. We went through some CMB basics, and we talked about baryon acoustic oscillations. And then we talked about how the CMB constrains H0 and how early and late universe solutions work by either modifying RS or DA. And then in the second part, we will talk about more how to realize the early dark energy model. Are there some questions?
You spoke in your calculations about that the universe is flat. Does this follow from the measurement in your derivations, or is it such an assumption that it is approximately flat?
Yeah, it actually follows from the measurements. Yeah, I actually earlier said curvature is constrained by the CMB, but actually it's not entirely true. You need to have the CMB and baryon acoustic oscillations in the galaxy data. So as you probably know, the same sound horizon that's imprinted in the CMB is also imprinted in the galaxy distribution. So we actually have a handle on measuring this ring here at different redshifts. So because what curvature does basically, if you imagine these here are light rays. In a flat universe, they simply travel in straight lines. But now you have, let's say you have a positively curved universe, then the light rays would travel more like this.
Would change your some of the observations, so you can you would have to put this in, because if you then say you change your model or don't change it, it could have some impact on this flatness business. This is what I always wondered about when we read all these papers. So it's a question
so I
of
think it's very well constrained by observation. So the CMB alone is not very sensitive to the curvature because it's only measuring the BAO ring at one redshift. But if you can measure the BAO ring at different redshift, you basically can constrain how the light rays travel. So we know that the light rays don't travel in this curved path because we have information about how big is this ring at different redshifts from baryon acoustic oscillations.
Thank you very, very much for this lecture and for preparing it. I have a second question. Maybe I didn't get everything rightly, but you mentioned at some point that one could derive the CMB by solving Boltzmann equations. And how does this, is this connected to what you said later about contact with measurement and with your formula you derived for this angel and for the speed of sound and all this? Is this, or where does this come in? I just didn't see it, or maybe didn't get it, or whatever.
Yeah, you're right. I was skipping definitely the connection there. So of course, when people do CMB analysis, they do not do this analytic computation because this is what people did in the early days of CMB. They basically just looked at what is the distance between these peaks, and then they compared the prediction of theta s to the distance of the peak. But of course, this is just one number. And nowadays people do full shape CMB analysis. So they do full forward modeling, basically forward modeling is maybe not the right word, but you assume some meta content and then you solve the full fluid equations and you predict the whole shape of the CMB power spectrum and not just theta s. So I just went through this derivation of theta s because I think it's instructive from like pedagogical way of looking at it, but this is not done anymore. But I believe this was done in the early days of the CMB when the data was not very good. And this is basically what people do now in galaxy clustering. They only infer the BAO scale. So they only infer one number from the observation and they compare it to the prediction from theory. But yeah, in the CMB analysis, what people do is predict the full shape and not just theta s. I just saw there's a question in the chat about how theta s is being used in measuring H0, because H0 appears the same way in the numerator and denominator. So it should cancel out. I mean, in principle, yeah, it appears in both numerator and denominator, but you have this integral over different redshift ranges. So basically here you have the expansion rate from today to the redshift of recombination, here from the redshift of recombination to the Big Bang. The sound speed doesn't have a strong dependence on h of z. So the sound speed is mainly dependent on the baryon to photon ratio. Also, you're asking about why H0 doesn't cancel out, but these quantities are measured very differently. And so the main part is that they are in different redshift ranges. Okay, then let's have a closer look at early dark energy. So early dark energy is most often modeled as a scalar field. So I want to have a small section about scalar fields in general and then expanding space-time. And just to get a small intuition about what a scalar field is, I have one slide about that. It's actually a very simple thing. It's just a scalar field assigns a number to every point in time and space. These are very common, scalar fields are very common. So for example, temperature is a scalar field, or density or pressure, because it assigns a number to every point in space-time. Or potential fields, like the gravitational potential and the electric potential, are also scalar fields. And the inflaton driving inflation is also most commonly modeled as a scalar field. So it's very common things in physics. And the action of a scalar field minimally coupled to the metric can be written as follows. So I will also just talk about this very briefly because William has given a lecture about inflation, and this is exactly the same physics, or almost exactly the same physics as inflation. So the action can be written as this integral over the whole space-time with the determinant of the metric here, and a kinetic term that's proportional to the derivatives of the scalar field, and a potential term. And from that action, one can compute the energy momentum tensor of the scalar field via this formula that comes from GR. And if we insert isotropy and homogeneity into this energy momentum tensor for the scalar field, we end up with this formula. And this is interesting because by comparing this energy momentum tensor of the perfect fluid, this energy momentum tensor of the scalar field with the energy momentum tensor of the perfect fluid, one can simply read off the energy density and pressure of the scalar field. So here we see that the part proportional to the metric is the pressure. So this here gives the pressure, the phi dot half minus V of phi. And then one can also, from having the pressure, one can read off the energy density. Now, inserting the energy density and the pressure into the first Friedmann equation and the continuity equation, one gets the evolution equations for the scalar field, where here in the second equation, one has the second term is the so-called Hubble friction, because it's proportional to phi dot and slows down the movement of the scalar field in the potential. And then there's the potential term here. And the second equation is nothing else but the Klein-Gordon equation for a scalar field in an expanding space-time. So basically the Friedmann equation reduces to the Klein-Gordon equation if one inserts homogeneity in the isotropy and the scalar field. So early dark energy is usually modeled as a scalar field, and here is a short history about early dark energy. Early dark energy models have already been studied before the Hubble tension emerged, but more in the context of quintessence models, so models of late-time dark energy. Then the axion-like early dark energy was proposed as a solution to the Hubble tension already in 2016, but it could only be shown in 2018 and 2019 with a proper modeling of the perturbations that it's actually possible to solve the Hubble tension with this model. And there are many versions of the early dark energy model, but here we will focus on the most commonly studied early dark energy model, which is the axion-like early dark energy model. Early dark energy is simply a scalar field in a potential V of phi, which boosts the expansion rate before recombination. And the potential was originally motivated from the axion, but here we take it as a phenomenological potential, because for the QCD axion, you have some very strict relationship between F and this normalization here. And this is not possible to solve the Hubble tension with this type of axion. So here we simply borrow the potential from the axion, but early dark energy has not much to do with the axion anymore. So this potential depends on this normalization factor V naught that is given by m squared f squared, where m is called the mass and f the decay constant of the field. And decay constant also appears here. And then there's the index n of the potential. For the standard axion, one would expect n equals 1. However, in a cosmological context, this doesn't decay quickly enough. And n equals 3 is the preferred value by the data, because it decays quickly enough and therefore doesn't affect late-time physics too much. And therefore it fits the data better. And in data analysis, one commonly fixes this index to 3 and only samples the other 3 parameters. So the 3 parameters of this model are the mass, the so-called decay constant, and the initial value of this scalar field in its potential. And there one commonly defines theta I as phi I, so the initial value of the scalar field divided by f, and n is fixed. And so let's have a look at the dynamics of the field. So the dynamics are governed by the Klein-Gordon equation. Initially, the expansion rate of the universe is very high. So this term, the Hubble friction term, dominates. And this field phi is basically frozen in its initial position. And in this phase, it behaves like dark energy. So this is very similar to the inflaton, which is also frozen in the potential and therefore leads to this rapid growth of the field. Then at some point, the Hubble expansion slows down and the potential term gets of the same size as the Hubble friction term. And this is when the field gets released and it starts rolling down its potential and starts to oscillate around the minimum. And one can show that in this phase, the field decays or redshifts away faster than matter. So the equation of state of this field is W equals -1 for redshifts earlier than this critical redshift. So the critical redshift is redshift at which these two terms have the same size. And this is when the field starts oscillating. So before the critical redshift, the equation of state is -1, like dark energy. And after the critical redshift, the equation of state changes, but the time average of the equation of state for n equals 3 is 1/2. So it redshifts actually faster away than a radiation, which would have W of 1/3. So you can see here on the right-hand side, the fraction of early dark energy as a function of redshift. So on the right-hand side are large redshifts, so early times, and at early times, this field grows very rapidly, like a dark energy component. Then the field starts oscillating in the potential and starts to redshift away. And what one typically does for the data analysis is one trades the particle physics parameters MF and θi for the phenomenological parameters FEDE, which denotes the maximum fraction of early dark energy at the critical redshift CC, and additionally the initial value of this scalar field. So in data analysis, typically people vary these parameters instead of.
I'm sorry, I have a question. Can I ask?
Yes.
M is the mass of what? Like actually, I joined in the middle of your presentation, so I didn't understand. Like M is the mass of what?
Yeah, M is basically a parameter appearing in this potential. The thing is, M is just an effective mass. So you can basically, the mass of a scalar field, if I remember correctly, is given by the second derivative of the potential by the scalar field. And only for n equals 1, M is actually the effective mass of this field. If you have higher n, it's there are some correction factors. But yeah, M can be interpreted as the mass of the scalar field for n equals 1.
Okay, thank you.
To solve the Hubble tension, one typically aims at about 10% of the fraction of early dark energy at its maximum. So let's have a look what these different parameters do. So the critical redshift, which is the redshift at which the field starts oscillating in the potential, it determines when the field peaks. So changing the critical redshift just changes the time at which early dark energy peaks. And then FEDE, of course, which is omega EDE at the critical redshift, determines the height of this peak. Now, θi is a little smaller effect. So the initial value, θi, since it's an angle, it is between 0 and pi, determines how fast the field oscillates when it decays. So if you look at the pink line, which is theta almost at pi, one has many more oscillations than if theta I has a small value. So if the field starts very close to the minimum, this would be this blue dashed line. The field doesn't oscillate very often and decays without oscillating much. So the closer theta I is to pi, the faster the oscillations. And then the index of the potential determines how fast the field decays. The higher the index of the potential, the faster the decay. So here, if you have a look at n equals 2, which is the blue dashed line, the field decays only very slowly. And this is very much disfavored by data sets. So n is typically fixed to 3, which is this green line here. So can early dark energy resolve the Hubble tension and fit all data sets at the same time? And I put together a very short review about constraints on early dark energy, which is definitely not complete. So of course, this question depends on the data sets that are considered. So I want to discuss some very commonly considered data sets here. Of course, the Planck CMB measurement, the temperature, the temperature E mode and E mode power spectra, and the lensing contribution. Then we also want to consider baryon acoustic oscillations imprinted in the galaxy positions. So before we talked about the baryon acoustic oscillations imprinted in the CMB, but these baryon acoustic oscillations, because they are imprinted in the matter distribution of the universe, in places where there's more density, there's a higher probability that galaxies form. So this baryon acoustic oscillations are also imprinted in the galaxy distribution, and we can measure them today. And then there's also redshift space distortions that are also often used in data analysis, which are basically an apparent distortion of this BAO ring because of the peculiar velocities of these galaxies. And this is actually a good measure of the growth of structure. And then there is the famous Pantheon and Schuss data set, which is the most competitive direct measurement of the Hubble constant, and it uses Cepheid calibrated type 1a supernovae. So what they do is they use parallaxes, typically from the Gaia experiment, to measure very precise geometric distances to Cepheids, which are pulsating stars in our own Milky Way. And with that, they can calibrate the distance luminosity relation, so they know basically how distant an object is depending on the luminosity. And they use these Cepheids in order to calibrate supernovae. So they look for galaxies that have both Cepheids and supernovae in them in order to use their information on the Cepheids to calibrate the absolute luminosity of the supernovae. And these supernovae are very bright, so we can see them very far away, far out in the Hubble flow. So they can be used to constrain directly the Hubble law. And the Hubble law, as you probably all know, states that the velocity, the recession velocity of an object is proportional to the distance of that object, and the proportionality constant is the Hubble constant. So now if we know the recession velocity, which is very easy to get because we can simply use redshifted spectral lines in order to get the recession velocity. And the distance we get from the distance luminosity duality. So once these supernovae are calibrated, one can directly compute the distance. So then the inclination of the slope gives you the Hubble constant. And using these data sets, one can analyze the early dark energy model. And one finds that these data sets prefer a fraction of about 11% of early dark energy and an H0 of about 71.5. So here on the right-hand side, you can see the 1D marginalized posterior. And I don't have much time to go into data analysis here because I think there's a lecture by Jürgen about this whole topic of data analysis. But yeah, in this 1D marginalized posterior, you can see the orange is a lambda CDM posterior. What EDE does is it increases the error bar on H0 and shifts H0 to larger values such that the tension with the Schuss direct measurement, which is the gray line here, is reduced to below 1 or 2 sigma. So if a model achieves the reduction of the tension below 2 sigma, people already speak about solving the tension because it's very difficult, basically almost impossible to find a model that shifts the central value of H0 to these high values. However, if you introduce early dark energy, not only H0 increases, but also other parameters shift. For example, early dark energy suppresses the growth of perturbations at early times. This is because early dark energy basically boosts the expansion of early times, so perturbations have less time to grow. And this leads, in order to compensate this suppressed growth, one needs more cold dark matter and a higher spectral index. And this is the so-called early integrated Saxe-Wolf effect. And this worsens the sigma 8 tension. And here a small aside on the sigma 8 tension. So sigma 8 is a parameter that measures the amplitude of density fluctuations in the late universe, and it can be computed by an integral over the linear matter power spectrum convolved with this top hat filter with a radius of 8 megaparsec over h. So sigma 8 basically smoothes the density field with a radius of 8 megaparsec and looks at the amplitude of the fluctuations at this length scale. Now S8 is simply a convenient combination of sigma 8 and omega m that's better constrained by weak lensing experiment. And it turns out that Planck prefers about 2 to 3 sigma higher S8 than weak lensing experiments like the dark energy survey, the kilodegree survey, or HST. And weak lensing uses the distortion of galaxy shapes because of gravitational lensing. So some foreground source lenses the background sources, and that gives one a measure of the matter distribution in the foreground. And this is a very good data set to constrain S8. So motivated by this increase in omega CDM and this worsening of the S8 tension, basically, many authors started to include large-scale structure probes into the analysis. So if one includes DS kits and HSC to this analysis, one finds very tight upper limits on the fraction of early dark energy and values of H0 that are perfectly consistent with the CMB, but they cannot reach the H0s of shoes. They're not able to resolve the Hubble tension. However, a more general picture evolves. So it turns out that actually, if you do not include shoes into the analysis, you find no preference for early dark energy at all. And if you additionally include large-scale structure probes, you get very tight upper limits on the fraction of early dark energy. So here on the right-hand side, if you look at the red line, you get, just from CMB data alone, you get a quite tight upper limit on the fraction of early dark energy. If you also include all the large-scale structure probes, your limit gets even tighter. And only including shoes into the analysis gives you a preference for early dark energy. However, many authors have pointed out that volume effects could affect these results. And volume effects, they are technical effects in the Bayesian analysis. And to explain volume effects, or also known as prior volume effects or projection effects, I picked this toy example here. In this toy example, assume you have an experiment that measures two parameters, alpha and beta. And this experiment gives you this black posterior here. Now, let's say you're more interested in alpha, so you might want to look at the 1D marginalized posterior in alpha, which is obtained by simply integrating over beta. So one integrates out this beta direction and obtains a 1D marginalized posterior in alpha. And the peak of this 1D posterior is in 0 here, and this non-Gaussian extension only leads to small asymmetry of this marginalized posterior. But now assume that you have a second experiment, this experiment 2, which is only sensitive to alpha, so it has this blue posterior here. If you look at the marginalized posterior, you might conclude that experiment 2 and experiment 1 are in maybe 2 or 3 sigma tension. But if you look at the 2D posterior, there's actually no tension, and you can safely combine experiment 1 and experiment 2 to get this very tight contour. So it might seem counterintuitive that actually, although alpha equals 0 and alpha equals 5 fit the data equally well, alpha equals 5 is outside of the 2 sigma confidence interval of the marginalized posterior. But this is simply a projection effect. Just because there's much more volume in alpha equals 0, alpha equals 0 is preferred from a volume perspective. And here in this example, it's very intuitive to understand because we can directly look at the full posterior, but in cosmology analysis, it's often very complicated because we have this large dimensional models with many parameters, so we cannot look at the full n-dimensional parameter space. So these prior volume or projection effect, they appear if the posterior is influenced by the prior volume. And reasons for that is that the data is not constraining enough for all these parameters. And this leads to a very flat likelihood surface. And that means that the posterior actually has a strong inference from the prior. And this can happen in models with many parameters. Also, the parameter structure of the model can generate large volume differences, and this often happens with nested model. And early dark energy is such a nested model because if you let the fraction of early dark energy go to 0, you recover the lambda CDM limit. So the early dark energy model is nested within the lambda CDM models. That means if FED goes to 0, your two other parameters that describe the early dark energy more closely, theta I and CC, they become completely unconstrained. And that's why there's much more volume in FED of 0 than at larger values of FED. And this can lead to a preference of FED of 0 in the marginalized posterior. And one idea to probe the influence of these prior effects is to use the profile likelihood. So what is the profile likelihood? It's a method from frequentist statistics to constrained parameters. And to construct this profile likelihood, one uses the chi-square or the -2 log likelihood. And one fixes the parameter of interest, which is called y here, to different values, and minimizes the chi-square or maximizes the likelihood with respect to all other parameters. So this gives the delta chi-square as a function of this fixed parameter. So the difference to the Bayesian approach is here we profile over the remaining parameters, the nuisance parameters, whereas in the Bayesian approach, one marginalizes or integrates over them. So basically, this is just a profile of the likelihood surface, whereas in the Bayesian case, one takes into account the volume of the other dimensions. And then from this profile likelihood, one can simply read off the 1 and 2 sigma confidence interval by finding the intersection of this profile likelihood with delta chi-square of 1, or for 2 sigma, the intersection of the profile likelihood with delta chi-square of 4. And if one applies this profile likelihood method to the early dark energy model, the MCMC, the Bayesian result, gave this very tight upper limit on the fraction of early dark energy and the low H0, whereas the profile likelihood actually prefers higher values of FEDE and a higher H0, which is consistent with shoes at 1.4 sigma. So this model is an example where Bayesian frequentist approaches give different results. And here in this left-hand plot, you can see different constraints coming from the frequentist approach. So the 4 top arrow bars use the profile likelihood, the bottom arrow bar use the Bayesian MCMC. And you see that the Bayesian MCMC prefers much lower values of H0 than the profile likelihood. This is the case here because the likelihood is not very constraining for all parameters of the EDE model. And this is because we're basically looking at an effect below the detection limit. And using both approaches can point to prior dependence or these prior effects. But with more data, both approaches should eventually agree. So then let's have a look at more data. There is the Atacama Cosmology Telescope, which is a ground-based CMB experiment that has higher precision on measuring the very high L, so the very small scale CMB. And this experiment actually prefers the EDE model over lambda CDM by about 2 to 3 sigma using a Bayesian approach. And they find H0 values that are consistent with shoes and very high fractions of early dark energy. And they find that this is driven by the ACT, TE, and EE power spectra. And the reason behind is still unclear why the Atacama Cosmology Telescope has such a strong preference for the early dark energy model, while the Planck telescope does not. So this is still an open question whether this is actually some measurement systematic. There's another ground-based CMB experiment, which is the South Pole Telescope. And the South Pole Telescope can also be used to constrain early dark energy. It also has higher precision on the very small scale CMB and polarization. And SPD is consistent with Atacama Cosmology Telescope, but with larger error bars. So it's also consistent with FED of 0. So no conclusion here. There's another probe that one can use to constrain the early dark energy model, which is the so-called Lyman alpha forest. The Lyman alpha forest is something actually very cool. So you look for a background source, typically a very bright quasar that is far away from us. Then the light from the quasar travels through the large-scale structure of the universe, and it hits some gas in the large-scale structure. And each time it hits some hydrogen gas, it collects an absorption line. And there's absorption line at different wavelengths of the spectrum of the quasar, because the light of the quasar is redshifted while it travels through the universe. So this is a very direct probe of the large-scale structure of the universe, or the gas in the universe, that can be used to constrain early dark energy. And using this Lyman alpha forest, one finds actually very tight upper limits on the fraction of early dark energy. However, one should be careful because there seems to be some internal discrepancy in the Lyman alpha data itself. So the ED constraints need to be taken with a grain of salt. But in this analysis, they find that both Bayesian and frequentist constraint disfavor the early dark energy model under this Lyman alpha forest dataset. Moreover, there is an updated Planck pipeline called the NPipe pipeline that uses slightly more sky area at high frequencies than the standard Planck pipeline, and it uses different analysis choices and has a reduced lambda CDM residuals. And it turns out that this alternative Planck pipeline gives tighter constraint on the fraction of early dark energy, both in a Bayesian analysis and a frequentist analysis. So this dataset really seems to disfavor the early dark energy model, of course, related to the reduced residuals with respect to lambda CDM. So it seems like there are more and more challenges for the axion-like early dark energy model. And even though we've been looking for a long time now, we don't find any clear evidence than the Hubble tension for the early dark energy model. So although early type models or early dark energy type models which increase the expansion rate prior to recombination still seem more promising models, we might need to be more creative in building these models, because there's lots of increasing number of observations that disfavor the early dark energy, at least the axion-like canonical early dark energy model. And this brings me to the recap of the second part of the lecture. So the reason behind the Hubble tension is still unknown. We talked about early dark energy, which is a scalar field in an expanding universe in a 1- cosine potential. Early dark energy has a complicated parameter structure with these 3 parameters that are very tricky to constrain from different data sets, and therefore care needs to be taken in the analysis. However, there seem to be more indications that the simple canonical axion-like early dark energy model is disfavored. But early dark energy type solutions are still the least unlikely ones, so we might need to be more clever in constructing these models. And yeah, here on this slide, I collected some references that I find useful and can also recommend. I really like these 3 books here, this Dodelson Schmidt and the Huterer and the Steven Weinberg, whereas the Steven Weinberg is more technical, so I think the other 2 books are better choice for first read. And there's a very good recorded lecture on the cosmic microwave background by Eiichiro Komatsu. And here are some useful reviews about early dark energy. So yeah, thank you for listening, and also thanks to Elisa Ferreira, Eiichiro Komatsu, and Graham Addison, who inspired lectures and notebooks, and thanks to the organizers.
Thanks so much. Very interesting, very nice presentation. So would anyone like to ask a question or comments? I think Natasha.
Yeah. A question. You introduced this scalar field for early dark energy, and my question is, if this would be real, are there any constraints for it concerning measurements in high energy physics, or has it been confronted with measurements? from the energy range which is necessary to the energy range which is already checked.
So in high energy physics, I mean, so what people have tried is to derive early type models from string theory, and they managed to do that, but I'm not an expert on that, and I don't know how natural it is. From what I understand, it doesn't naturally come out of any theory. And it's taken as a phenomenological model, so we're like, there's no, yeah, we observers
No, I
basically,
mean-
yeah. What do you mean by high energy constraints?
I think of observation, not of that it does not come out of any series. That's a second problem. But the first problem, can one exclude it from observation, or because some energy ranges have already been checked and some not, and yeah. Are there any considerations about it?
Oh, you mean with direct detection experiments?
Yeah. That one can have,
Yeah.
this should have been
Okay, yes.
already appeared in CERN or not, or could still appear.
Okay, yeah, so the thing is, this field is very light and it appears only in the very early universe. So because it redshifts away faster than radiation, the density of it today is super low. So we have, first because it's super light, and then because it's already redshifted away, we will not be able to detect it directly.
Yeah, not naturally, but in the high energy particle detectors, they try to find new fields in particles at high energies, so artificially.
Oh, you mean by collision experiments to produce this?
Yes.
Right, that would require some coupling between the early dark energy model and our standard matter. And so in the way that we are looking at this model, it's not coupled to any matter. So it's really, sometimes people talk about decaying early dark energy, but in that sense, it's not decaying into other particles, it's just staying there and redshifting away. So it's just getting diluted out. So it's not coupling to any other particles, or at least not in the canonical form.
But still one has a mass energy equivalent, so something, or you say it's so high energies that this range is not checked yet, and it's still open.
Right. The thing is, if you want to produce it in a particle collision experiment, you need it to couple to the particles, right? I mean, I'm not an expert on that, but I think the thing is, if it's not coupling to any of the standard matter, you cannot produce it in an accelerator.
There's a question in the chat. Anatoly?
Yeah, so the question is, does ED have any effect on the presence, or can it solve the problem of the presence of supermassive black holes in the relatively early universe? The thing is, people have thought about questions like that, also mainly in the context of the JWST. So JWST saw these very early, very massive galaxies, where also people don't really know how they formed. And that might be a bit related to people don't really know how the supermassive black holes formed in the early universe. And one side effect of early dark energy could actually help with these two problems, because as we said, early dark energy, because it suppresses the growth of perturbations at early times, it favors models with more dark matter. And of course, having more dark matter helps to form very early, very massive galaxies. But the studies that looked at these very early massive galaxies found that actually you need a lot of early dark energy and you need a lot of more dark matter, which was completely ruled out. So I don't know much about, people looked about supermassive black hole formation, but I assume you would also need a lot of early dark energy, which would destroy a lot of other observations.
Thank you. So I think there's Priya.
Thanks for the nice talk. I have two basic questions. In slide number 117, you said you use Fast-Friedman equation and substituted everything there. But instead of Fast-Friedman equation, if you use second Friedman equation, do you think it is also consistent, right? Yeah, like this equation hs square equals to something. You said you substituted in first Friedman equation both energy and pressure, and you obtained this one. But if you substituted everything in the second Friedman equation, so do you expect the same things or different?
I think you're right. Yeah, the thing is, the three Friedman equations, they are of course not independent. Just two of them are independent. If you use either two of them, you would get the same set of equations. So I can't remember from the top of my head what happens if you substitute in a different one, but I assume that you will definitely get the same.
Because I'm thinking there you have also derivative of h. So it may be like a differential equation, something like a differential equation come out or something like this. I don't know.
Good question. Yeah, I can't remember out of the top of my head what would happen there. But you will, yeah, the thing is you will always get the same set of equations, even if you formulate it more complicatedly, because only two of the three Friedman equations are independent.
Yeah. Okay, thank you. And another question is related to the luminosity distance. How can I see like how this equation of motion is connected with the luminosity distance? Like there is a formula in maybe slide number 141. So you explain F equals to something L upon something, but I don't understand how, if I want to connect the equation of motion with the luminosity distance, how do I see it?
So the equation of motion of the early dark energy model.
Yes.
Yeah, that's the thing. So it's too complicated to connect analytically. So what happens is you put the early dark energy model in a Boltzmann solver with all the other matter components, and you need to solve this numerically so that you get predictions. You basically, from your Boltzmann solver, you get predictions of H0. But you cannot, it's too complicated to relate that analytically. Should I just explain the notebooks for 5 minutes? So I put on my website, I put the 2 numerical exercises that you can use to get more familiar with class and class EDE. So you can just open these notebooks. The only requirement is that you have a Google account. If you don't have a Google account, I also have the notebooks saved on my GitHub, so you can just download. But if you do that, you have to install the codes yourself. If you have a Google account, you can just open this and you copy this. So if you open my Google Colab, you have a button here to copy this to your Google Drive. And once you have it on your Google Drive, you can simply just run each of the cells by pushing this play button. And there's some description and some exercises on how you can use class, and it's basically a step-by-step guide. You're not required to know much Python because the exercises can be done mainly by copy-pasting commands. And there are 2 notebooks. The notebook 1 is more basic, and the notebook 2 actually you can download. You will download data from Planck and actually analyze the CMB power spectrum, and then you will also download data from shoes and you can analyze it together using class. So yeah, if you have time, please give it a try, and if you have questions, you can email me at any time.
Thanks so much. Thank you again. It's a big help for everyone here and also for people who see the video later on.